Do you want to know how to make a super sturdy gantry out of aluminum and why steel is not the best material choice for hobby CNC routers? In this video, I will show the design and assembly of my ultra-rigid gantry with a hidden and dust-protected servo motor. You can see how to fill extruded profiles with epoxy granite and why, and if your CNC stands in a corner and you have difficulties to reach each grease nipple, I might have a solution for you. Hello and welcome to my channel. This is part 4 of my DIY CNC router build series. In the last video, I finished the machine base and showed how to build and precisely adjust the machine on an uneven workbench. In case you haven't seen the first parts yet, I have linked the videos in the description below. One of the weakest points of gantry-style routers is the lateral stiffness of the gantry. It has a direct influence on vibrations, noise, tool life, surface finish, and most importantly, part precision. Now, the easiest way to build such a router is to simply bolt two plates to an extruded profile and the linear blocks. Done. But this is as well the worst design in terms of stiffness, especially when the side plates are tall. Now, I've seen people trying to address this issue by using steel plates instead of aluminum, because steel is a stronger material than aluminum with a 3 times higher Young's modulus. But steel is as well almost 3 times heavier than aluminum, and for a dynamically moving gantry, the mass is an issue as well. What is far more important, however, is the fact that material thickness has a much bigger impact on bending stiffness than material because of the second moment of area. If you take a 10 mm thick steel plate as a starting point, a 50 mm thick aluminum plate has already a 12% higher bending stiffness, but only half the weight. And a 30 mm thick aluminum plate, which has more or less the same weight as a 10 mm thick steel plate, has already a 9 times better bending stiffness. Another weak point of this design is that you lose the width of your Z-axis on the travel. In other words, if you want to have 800 mm of travel and your Z-axis is 200 mm wide, your gantry already must be at least 1 meter wide, which further reduces the overall rigidity. This issue can be addressed by bolting the gantry beam in the recess on top of the side plates and to connect them with angle brackets. With such a design, the span between the side plates can be just a little bit wider than the work area, but the overall rigidity depends highly on the strength of the angle brackets. I decided to go with my design in a completely different direction, with a C-shaped gantry beam milled out of a solid 25 mm aluminum plate, which is bolted to the also 25 mm thick side plates in a crosswise pattern from the front and the inner sides. With this, I can eliminate completely the need for additional brackets and, in combination with the dual rail design on the machine bed, achieve a very good lateral stiffness. There's literally no area where the side plates can bend. However, such a large plate does not have a good torsional rigidity, which is why I have added a 200 by 800 mm extruded profile, which is bolted from 3 sides between the side plates and the gantry plate. Milling each part starts for me with the selection of the required tools and placing them in a separate rack in the sequence of use. I change tools by hand because, as you can see, I have plenty of them and simply no space for an ATC magazine with 120 tools. And a smaller magazine doesn't really make sense to me because I do not have large production runs, but almost only one-off prototypes. So loading the magazine each time with the right tools and telling the control software which tool is in which pocket is effort as well. And in addition, I really prefer not to run the machine unattended. And here I start with the large gantry plate. I first mill the entire outer shape with an 8 mm single flute end mill, mainly because of the full slot operation when cutting the C shape. The 930 by 390 mm large plate is fixed with vacuum holding during the entire operation. There are two long spacer bars on the plate which hold the linear rails. I drilled them and milled their outer shape together, but left some stock on the mounting surface of the rails because I milled them to their final dimension only after I bolted the spacers to the gantry plate. After the spacers have been added and milled to final shape, I had to add 4 M8 threads to the inner side of the C. This was only possible by hand, so I made a drill jig out of some offcuts and put the cordless drill to work. A long time ago, I started to power tap threads in aluminum, and especially with bigger threads like M6 or like here M8, you don't have to be afraid of breaking a tap, but it saves so much work. And with this, the biggest part was done, and I started with the side plates. They are quite feature-rich, and each one had to be machined from 5 sides. I will not go into every little detail here, but rather show you a few impressions.
I've already mentioned in the first video of this series that one of the main constraints that I have is the available space. So a directly coupled servo on the gantry was out of the question because it would stick out like a Thor's thumb, consuming too much wasted space in the enclosure. That's why I went with a belt and pulley solution. I use high-quality timing belts from Gates with an HTD5 profile and 36 teeth pulleys with a taper lock bush. I've used this combination on several builds in the past and made very good experience with it. However, I always try to keep the belt length as short as possible, so placing the servo behind the gantry was not an option either. To solve that problem, I had to extend the servo shaft and mount the servo directly to the gantry side plate. I already had this design on my previous router and it worked flawlessly. The shaft extension is a small sub-SE consisting of an extension shaft, two bearings, a bearing block, and a coupling. The shaft has a bigger diameter in the middle for the two inner rings to rest against. One bearing is then fixed by the coupling, and the other bearing, and therefore the entire shaft SE, is fixed by a plate on the outer side of the gantry where the belt and pulleys are located. The only problem with this design is that I have to mill a recess in the extruded profile for the motor, and that the overall length of the profile has to be very precise. But more importantly, the profile has to be filled with epoxy granite in order to improve the dampening properties of the whole gantry. Even though I only use heavy versions of these profiles, it is better to fill them. On the other side, I wanted to avoid making it unnecessarily heavy, so I went with a mix of epoxy and Aeropor 180, also because I still have some leftover from a previous build. Aeropor 180 is a very lightweight artificial aggregate, which is basically tiny hollow glass balls. It doesn't have to be dried and can be mixed immediately with the epoxy. And the density of the whole mix is around 0.6 gram per cubic centimeter. Because of the cutout for the servo, it was kind of hard to make a funnel for the fillings, so I just did it by hand and compressed it with a long wooden stick. This was a bit tedious because I also had to work around two alu tubes that are placed in the middle, so I'm still able to route cables through the filled profile. But once everything is hardened, both ends are sealed with epoxy. Why all the effort? Well, listen for yourself. I believe the result speaks for itself. And with this, all the major components were made and I started the assembly. First came the side plates. They have two 6mm holes for dowel pins machined precisely into the inner sides. The pins rest on the ground surface of the linear blocks and ensure a perfect alignment of the side plates. Once they were attached, I slid the gantry plate in place. For this, I squished the side plates at the top with a woodworking clamp to make this process a little bit easier. And this was the only time that these plates actually saw some bending. The gantry plate is then bolted to each side plate with 2 M8 bolts from the front and 4 M8 bolts from the inner side. And here you can actually see why these outer ribs of the gantry plate are not longer all the way down to the bottom of the side plate. There is simply no access for more bolts in this area. At this stage, the gantry runs nice and freely without any play, but as well without any binding or high spots. Next, I had to assemble the plate which runs under the machine bed and connects the side plates with the ball screws. For that, I had to raise the, at this stage, already some 250 kilo heavy machine using the help of my wife and some good old physics. Technologia! The reason I bolt this from the bottom and not from the sides, which would be much easier, is that in case the plate is a hair too short, this would put a lot of pressure to the linear blocks and cause them to bind. Once this plate is in place, I can connect the bolt screw nut housings. This is an iterative process of fixing and losing the bolts a few times in order to make sure that the housing sits perfectly parallel to the nut and to the plate. As you can see, I have done that at the far end of the fixed bearing side of the bolt screws, because only after this step has been completed, I'm able to finally fix the bearing blocks on the floating side. For this, I lose the bolts again and push the entire gantry with already connected bolt screws to the other end, which has the effect that the floating bearing housings align themselves. And then it was time to complete the gantry. First, I assembled the bolt screw, starting with the floating bearing side. For setting the correct distance on the floating bearing side, I use a pair of gauge blocks. But this is just a preliminary setting. The final adjustment of this side will be done later in the same fashion as you have just seen. Once the ball screw was in place, I could mount a servo with the extension shaft unit. This is bolted from the outside through the gantry side plate into the servo. There are versions of this JMC servo with an M5 thread in the front, but mine, unfortunately, came with 5.5mm holes. So before mounting the servo, I had to make a new front plate and exchange it with the existing one. In order to be able to slightly adjust the timing belt tension, I have 4 M6 grub screws in the gantry plate that can push against the shaft unit. The through holes in the side plate are of course long holes to make this happen. Then the pulleys and the timing belt are mounted, and after adjusting the correct tension, the entire unit is fixed. But then I had to remove everything again in order to fit the outer plate. And this process was in fact not really well thought of, and I added later on 4 more holes to access the fixation bolt, even with the plate mounted. Finally, the coupling is fixed to the servo shaft and the outer plate is added to the gantry. So the only thing that is still missing was the filled profile. But before adding the profile, I had to make it dead flat first. These profiles always have some tolerances, and although this was a better one, it still was twisted by roughly 0.2 millimeters over the entire length. Because there's no way you can access T-nuts during the assembly in order to move them into the correct position if needed, I have designed T-bars which go into the slots and have the correct thread spacing. And once they are added, the prepared extrusion slides in place and is bolted from the front and from the sides with a zillion M8 bolts, adding an incredible rigidity to the entire gantry. And this brings me to the last subject of this video, the greasing concept. As I mentioned before, this router stands in a corner and has a full enclosure. So the access to everything is just from the front. And on my previous routers, it was exactly the same, and I had always problems to access the grease points of the linear blocks and ball screws, especially on the side close to the wall, because there is also the drag chain in the way. So with this new build, I designed everything in a way that all grease points are facing towards me when I stand in front of the machine, which is in fact the left side of it. To achieve this, I drilled a lot of through holes in the gantry side plates and as well in the cross plate, which holds the Z-axis. The blocks on the gantry side are greased from the top, which means there is an O-ring between each block and the side plates. The cross plate has several fittings, which in turn are connected to the blocks and ball screw nut with 4mm pneumatic hose. I prefer these push-in fittings for greasing because I run during the greasing process a small program which slowly moves the axis back and forth for a better grease distribution, and I made the experience that this works for me better with a fixed line from the grease gun to the fitting. And with the linear rails, crossplate, and a few covers attached, the gantry assembly is almost finished. There are still a few covers and the drag chain guide on top of the gantry missing, but so far so good. Let me know in the comments below what you think about this design and whether you like it or not. In the next video, I will assemble the Z-axis and explain the pros and cons of fixed rails versus moving rails on the Z-axis. If you liked the video, give it a thumbs up, subscribe to the channel and hit the notification bell. Stay tuned and see you next.